Lesson 5, what we call many body problems. What we mean by that is, hey, what if you got more than one mass? Specifically, to keep it fairly straightforward at this stage, what if you have more than one mass but they're attached with a rope or a string? So in these problems, we have several objects connected together by strings, and here's the key concept, Enzo, you need to realize. Here is my many body system right here. I have two masses connected by a string with a little pulley in between them. Here's the idea. If I'm accelerating this mass in my hand to your left at 2 meters per second squared, what is this bottom mass accelerating up at? 2 meters per second squared. What we're going to get you to realize, Abe, is if they're attached with the same piece of string, they must be accelerating at the same rate. Oh, but Aaron, we're going to say no cheating, no doing this. Okay, so no giving the line a big jerk or a big yank and having the system become no longer stable. All right? So we'll start out with an example here. Example 1 says, find the acceleration and the string tension, and there's more than one mass. Our solution is going to be, we're going to temporarily, Greg, in our winner minus loser, treat this as one big mass, even though there's two separate masses. We're going to say, you know what, Brad, mathematically, physics-wise, attached by a string, we can treat them the same way. I'll show you what I mean. First thing we're going to do is we're going to do a free body. Well, okay. Matt, technically, a free body diagram would be if I represented them each mass with a dot and rewrote everything. What I'm going to do instead of a free body diagram, I'm going to take a shortcut. I'm actually going to label the diagram that they gave me with the forces. So I'm going to start with this 3 kilogram mass right here. What are the forces acting on it? Get the obvious one. Now, normally I just write mg, but since there's more than one mass, I'll call this m1g, and I'll call the second mass m2. And generally, my rule, Amanda, is I label the masses from left to right. So the first thing that you see with your eyes will be M1. The second thing will be M2. That way all of our work looks the same. You don't have to, but I generally do that. Is M1 sinking into the ground? No. Is it lifting into the air? No. Then Cole was correct. There must be a normal force. And you know what? Since I got more than one mass on the surface, I think there's going to be more than one normal force. I'll call this normal force number 1 to go with mg number 1. By the way, what's the friction involved in this question? What does it say in brackets underneath the diagram? 0. So we're on ice, if you're using your imagination. Which way is this 3 kilogram mass going to be accelerating? Well, which way is this whole thing? If you look at the picture, which way is this whole thing going to be accelerating? If you put two masses on ice and you tug with 20 newtons to the right, which way are they going to accelerate? So that 3 kilogram mass has to have an unbalanced force to the right. Not the 20, though. A lot of kids want to say, well, the 20. No, is the 20 touching the 3 kilogram mass? Nope. Then don't be putting it on the 3 kilogram mass. What is touching the 3 kilogram mass? This piece of string. And we're going to give the force from a string a fancy schmancy name. We're going to call it tension. The 3 kilogram mass is being pulled to the right by the string. And those are the three forces. Oh, if there was friction, I would have, don't write this down, I could add one more in that direction. No friction, no big deal. It wouldn't make my equation that much tougher. It would make my equation a little bit longer. Let's go to mass number 2. What are the forces acting on it? Get the obvious one. Darn right. I'll call it M2G. I'll call it normal force number 2. We have an applied force of 20 newtons. Someone's pulling. Oh, there's one more. Tension in the opposite direction. And this is forces come in pairs, Newton's law. This is the first time forces come in pairs, Newton's third law has appeared, because it's the first time we've had two masses where we can actually have both of them showing the interactions between them. Okay? So I wrote solution. We're going to treat this as a single object. We're going to write a force equation. I'll show you what I mean. Take a look at this. Vertically, can you see everything is balanced? Meh. Boring. But horizontally, in the direction of along the string, who's winning? Applied. Anything that ends up pointing to the right then, now I've decided is going to be winner plus. Anything that ends up pointing to the left then is going to be loser. Sorry, I didn't mean to look at Nick. Minus. Okay. Who's winning? Now, I'm going to start with that. I'm going to walk along the string. The next force that I run into as I walk along the string is tension. Tension pointing which way? Loser. Oh! But I run into another tension pointing which way? Winner. Are there any other horizontal forces? Mr. Duke, what about like normal forces? MG, they're all in balance. I don't care. Doesn't appear to be acting on the string. That's it. Now, normally, don't write this down, Chris. Normally, don't write this down, folks. I would then say, the only problem is, we've looked at more than one mass. We've looked at more than one mass. So instead of winner minus loser equals MA, it's really winner minus loser equals the mass of both of them times A. The mass of all of them times A. There is, but the symbol isn't much shorter than writing both or all. It's easier just to write both. Or all, if there's three masses or whatever. Oh, what else do you notice on the left-hand side? Look at the equation on the left-hand side. What do you notice here? What cancels out? Okay, everybody, put your pencils down. Everybody, put your fingers together like this. Everybody take a deep breath. Everybody let it out. You know why? We're getting rid of tension. I always like that. So relaxing to get rid of tension. Oh, I wanted to cross it out, Mr. Duke. So let's do that again. Don't erase it. I want to show that it actually was there, but it turns out when you have plus tension, minus tension, gone. In fact, my equation simplifies to F app, the applied force, equals the mass of both times A. How would I get the A by itself? Divide by the mass of both. The acceleration of this system is going to be F applied divided by mass 1 plus mass 2, the mass of both of them, which is going to be 20 divided by 3 plus 2, which is going to be what? Thank you for doing it in your head and recognizing that it's really 20 over 5. My block F's had like 10 kids reaching for their calculators. Oh. Yeah, him. Oh, disgusting. This is 20 over 5. You know what? This is going to accelerate at 4.0. I'll go to 2 sig figs since it looks like my data went to 2 sig figs. Meters per second squared. So it said find the acceleration, check, and find what? String tension. I can't use this equation to find string tension. I can't look at all of the masses to find string tension because when I do that, the tension will cancel. So what I'm going to do instead, Brad, I'm going to look at one mass. I'll look at the 3 kilogram. What were the forces acting on it? Do you remember? We had gravity down, normal force up, and tension. If I just look at this mass, who's winning? Who's losing? It's a trick question. No one. And now we're just looking at one mass. So instead of winner minus loser being the mass of both times A, it's going to be the mass of one guy times A. This tells me the tension in the rope. I go look at a single mass. How big is mass 1? 3. What was the acceleration? 4. How many newtons of force, because tension is a force, and this is mass times acceleration, how many newtons of force must this rope be able to hold for this to work? If it can't hold 12 newtons, it'll snap. Oh, and if it can hold more, we got plenty of room to play with. Now here's the nice thing, Jamie, supposing instead of the 3 kilogram mass, supposing for some reason, because you're different, you are, you decided to go with the 2 kilogram mass, the right hand mass. Okay. What were the forces acting on the 2 kilogram mass? We had M2G, normal force number 2, F applied, and tension. If you were to write a horizontal force equation for this one, it's going to be winner minus loser equals, and Maddie, now we're looking only at one mass, so it's going to be M2A. Why M2? Because that's what I just did the forces for, right, Nick? Right. If I wanted to get the tension by itself here, I think the easiest way would be to plus the tension to that side and to minus that to that side. Yes? I'd get this. F applied minus M2A equals tension. In fact, I'll get tension equals, what was the applied force? 20? Minus, what was mass 2? 2. What was A? 4. Hey, what does that work out to? The same as before. Oh, yeah, of course. It's the same piece of rope, so it must have the same tension. So the nice thing, Jordan, is it doesn't matter which mass you look at, although I'll guarantee almost always one of them will be less work. In this case, in this question, the way this one was set up, that was less work. We didn't have to rearrange an equation at all. Here, we'd do some math. But you'll get there just fine. Many body problems. Give me more than one mass, I'll treat it as one mass temporarily. Tension will cancel, although I'll always write it just to remind myself where it was, because I might need it later on to find tension. Fact, we could even go with a hanging mass. Something hanging over a cliff, like this picture here. If we have a hanging mass and no external force, well, use your imagination. First of all, what's the coefficient of friction here? So we're on ice. You know what? If this is on ice, this is going to pull it off the cliff. Right? If you were standing there on ice trying to hold up a person, that person would drag you over the cliff. I'm positive, Jordan, this is going to accelerate this way and that way. This is why we went to the tug-of-war analogy, because this guy is accelerating to the right, positive. This is accelerating down, negative. We'll just decide who the winner is and make that be positive. Example 3 says, identify the net force, find the acceleration and the chord tensions. Okay. Let's label our diagram. What are the forces acting on the 2 kilogram mass? Get the obvious one. Darn right. Since there's more than one mass, I'll call this M1G. Is this sinking into the ground? Is it flying into the air? Must be a normal force in the opposite direction. What else? There's a rope. That's it on mass number 1. What are the forces acting on mass 2? Get the obvious ones. I'll call that M2G. What else? Must be tension up, because it's also attached to the rope. That's why it's not in free fall, by the way. Tension is what's slowing this guy down. Amanda, you agree with me that this whole thing is moving that way? Yes? So here's my question, folks. Which force is the winning force then? Which one? There's more than one. Can you give me what I wrote as in a little equation right there? Aaron, read that. Read that out. Okay, ready? Because when you say gravity, first of all, gravity is not a force, it's an acceleration. Force due to gravity. Which one? How about next time we just say, who's winning? M2G. Yes? Less work, more clear. Yes? Who's winning? So anything that ends up pointing down when I follow it through the string is going to be winner positive. Anything that ends up pointing in the opposite direction of M2G up is going to be loser negative. My equation is going to look like this. Winner. And now I'm going to walk along the string. When I do that, first thing I run into is the tension pointing up. Loser. Oh, I didn't mean to look at the force, right? Keep walking along the string. I run into this guy, which I might be tempted because it's to the right to say is positive, but when I follow it all the way through, actually no, it's going to, oh, it is positive. It's a winner. Are there any other forces along the string? Kelly, any other forces along the string? Any other forces along the string? Say it with a loud, authoritative voice like you know what you're talking about because you're correct. No. There's some vertical ones. I don't care. They're balanced. So this is going to equal... Now, Kelly, normally it would be... But since I've looked at two masses on this left-hand side, because that's a force from the second mass, I'm dealing with more than one mass. It's going to be the mass of both times A. Ah, great question, Cole. Once again, we're in our magic physics world to make the math nice. Our ropes have no mass, and our pulley is massless and frictionless. Thank you. Good point. I'm in my happy place. Why I'm in my happy place? I like that. Oh, let's get the A by itself. Because it said, identify the net force. We just did. There's our equation. Then it said, find the acceleration. How do we get the acceleration by itself? Sorry? Divide which one? Yeah, mass of both. So if I hear you correctly, A, but I think I do, the acceleration is going to be m2g divided by m1 plus m2, mass of both. Sorry? Messy writing, I know. M2G, right? Gravity is what's putting this whole thing in motion, but both masses have inertia. They're slowing it down. That's why you're dividing by them. Mass 2, 4, G, 9.8 over mass 1, 2 plus mass 2, 4. It's going to be 4 times 9.8 divided by 6. I don't think it's 6.5. Isn't it 6? What? Isn't it 6.4545454? Or remember? No. What do you get? Sorry, I'm misremembering. That's the wrong one. 6.53333. Okay, that's. I thought you said 6.5 repeating. I was going. I don't recall. There you go. Units. It's an acceleration, so it must be meters per second squared. So example 3 said, identify the net force, check, right there. Find the acceleration, check, right there. And find what? Tension. To find the tension, I'm going to look at one mass. Which one? Doesn't matter. I'll get the same answer for both, although one will be less work. Greg, do you want me to find the tension using mass 1 or mass 2? Mass 2? The hanging one? Okay. I'm actually going to do both. So let's draw a little line down the middle of our page. We'll do mass 2, finding tension on the right. We'll do mass 1 on the left, and if we get the same answer, we know we're right. On a test, I would only do it one way, but if I had time after the test before I handed it in to check my answer race, I would certainly use the other mass to find a tension. Yeah, I know I'm right. Or, something's wrong. Okay, so using mass 2, Greg, look only at mass 2. Who's winning? M2G is the full force. M2G. Who's losing? Tension. And that's going to equal M2A. Not the mass of both anymore. We're looking at one mass, Cole. To get the tension by itself, Cole, I think I would plus that to that side and minus that to that side at the same time. Is that okay? So if I hear you correctly, my friend, you're saying tension is going to be M2G minus M2A. Mass 2 was 4. G was 9.8 minus mass 2 was 4. A was 6.53, Mr. Duick. 6.53. What do you get for the tension? 13.1? 13.1? Units for tension. It's a force. Newtons. Now Greg said, I'm going to use mass 2. Let's suppose Kayvon said, I'm going to use, Mr. Duick, mass 1. Sorry, you guys are still writing too fast. Kayvon, if I use mass 1, look at my picture for mass 1. Who's winning? Tension. Who's losing? Trick question. Oh, in fact, Greg, mass 1 gives you a much nicer equation. Mass 1 gives you M1A. What was mass 1? 2. What was A? 6.53 repeating. And in fact, if you put in a few extra 3s, I'll bet you get to 3 or 4 sig figs, exactly what Doug said. I bet you do get the 13.0. Yes? 13.1 newtons. Janaya, same answer. Very nice. I like this. Doesn't matter which one. Which one was easier? Generally, I look at whichever one has tension winning. That's usually easier unless it's got a whole bunch of other forces on it. That's usually my approach. Turn page. Oh, I did this last time too. Apparently here, to find tension, isolate one mass, I'd actually left room on this page to do what we did right here. But I kind of like this mass 1, mass 2 contrasting little one there. So to find tension, isolate one mass. Then I wrote at the bottom of this page, for problems that involve friction, we can still use the system approach to find acceleration, but the tension calculations are tricky. We'll do this in Physics 12. I can't remember why I said we'll do this in Physics 12. I may do this with you guys in Physics 11. We'll see. Friction doesn't make things that much harder. You just have one more loser. Or if there's 2 things with friction, 2 more losers. And once you have the direction correct, friction is mu times the normal force. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. It's doable. Makes your equation longer. Not really tougher. There's a special kind of many-body problem that we like to talk about. It's called the Atwood machine. The Atwood machine is a pulley system as seen below. The Atwood machine is this thing here. When one goes up, the other goes down. When one goes up, the other goes down. Except the pulley, like Cole has already pointed out, is massless and frictionless, to make the math easy. Oh, and the ropes have no mass. But this is a nice theoretical multi or many body problem analogy, and also it's something you deal with all the time. This is an elevator. You see, every single elevator has the elevator, but somewhere else they have a counterweight which weighs the same as the elevator when it's empty, plus a couple of extra people. And the reason they do that, Chris, is this way the motor, which is where the pulley is, only has to take into the weight of the people, not the actual car itself. It only has to lift the difference between the two masses, which means you can get away with a way smaller motor and you use way less power. In fact, mass 2 is called the counterweight. Example 1. Here's our first thought experiment. Equal masses are placed on both sides of the Atwood machine, and one mass is lifted higher. So here's my Atwood machine. Look up, and I'm going to do this. Lift one mass higher. And then I'm going to let go. Dunk, like that. If this was massless and frictionless, if this was greased or ice, what would happen when I let this go? Would A, nothing happen, the system remain at rest? B, when I let this go, would the higher mass fall down till it reaches some kind of equilibrium point? Or C, when I let this go, will the higher mass go up if this was frictionless? Once again, Enzo, we're going to choose this opportunity to vote. Once again, how high you hold your hand is how sure you are of the answer. I'm positive! I'm pretty sure. Duke will make fun of me if I don't vote, so I'm going to just pick the one that were my friends with. Okay. Okay. Who says A, the system remains at rest? No, don't make your argument. You got to pick. You can defend your argument later. 2. Who says B, the higher mass is going to fall down? Sure. 2. Who says, nah, higher mass is going to go higher? 6, 7, 8, 9, 10, 11, 12, 16. Who didn't vote? You didn't vote? I know. I'm going to get to you next. Which one? You going to go B? Which one? There's a few of you others that didn't vote, but yeah, I know. You're going to go A. So here's the rule. You can either defend your answer as being correct, or you can attack someone else's answer as having to be wrong using principles of physics. You can attack or defend. What do you think? Who's right? Who's wrong? Convince me. Yeah.
There's no way the higher mass could fall because gravity on the other one is much more.
There's no way the higher mass could fall because gravity on the other one is much more.
I mean, it's farther down, so I mean, there's more.
I don't know what the word you're looking for is.
Tension.
Yeah.
Well, he said the pulley may have no mass. He didn't say that the rope would have no mass.
For the purposes of this, for the Atwood machine, we're talking about massless, frictionless ropes and pulleys. You know what? Let's see if we can. Nope. About 5 more minutes you can. Let's see if we can figure this out. Let's see if we can reason our way to the answer. Let's label our diagram. I'm not going to do a free body diagram. I'm going to label the actual diagram that they gave me. So I'm going to start with the higher mass, and I'm going to say, what are the forces acting on the higher mass? Get the obvious one. mg. What else? Tension. Here's the lower mass. What are the forces acting on it? Get the obvious one. mg. Mr. Duick, how come you didn't call it m1 and m2? Does the question say the masses are the same? Yeah, I'll just use m for both of them then, yes. What else? Now, it looks like most of you feel C is the correct answer. So if C is the correct answer, if the higher mass is going higher, then this must be your winner. Is that what you guys are saying? Yeah? So anything that ends up pointing down on the right-hand side is going to be winner plus. Anything that ends up pointing up on the right-hand side is going to be loser minus. So let's write an equation. We're going to have winner plus, loser minus. Now, you might be tempted to say, well, this tension's pointing up, so is this one, so this is a loser. But follow this one around. It ends up pointing down, yes? It ends up becoming a winner. And in the same way, you might be tempted to say this mg here is down. It's a winner. Actually, follow it, follow it, follow it, follow it, follow it, follow it. Which way does it end up pointing when it gets to this side? It's pointing down right now. Which way does it end up pointing when it gets to this side? Up. Loser. And that's going to equal the mass of both of them times A. Aaron, what did you say? I heard you say something. I heard you say, I heard it. What does the left-hand side, the whole left-hand side work out to? So you're saying this ends up being 0 equals 2m times A. Now, for this to be 0, are the masses 0? Nope. Nope. No. Mass is a scalar. Mass plus mass is 2 mass. No such thing as a negative mass. So for this to be 0, are the masses 0? No! What has to be 0 on the right-hand side for the left-hand side to be 0? So what's the correct answer? Why? There's our explanation. You have no unbalanced forces. It's Newton's first. In a more complicated situation, Jamie, yes, but it's Newton's first. If you have no unbalanced forces, then when you leave it alone, it wants to stay as is, which means it's going to stay at rest. Or if you raised it at a constant speed and then let go, it would want to keep going at a constant speed in our massless, frictionless, imaginary world. No, not larger mass. It does say equal masses. First two, that's the key. Of course, I can't imagine you not reading the first 2 words of a question. Okay. Last one, and then I'll let Greg go, but we'll finish this one first. In the diagram below, it says, assume mass 2 is bigger than mass 1. So this time, the higher mass does weigh more. You know what? Let's even make up some numbers. Let's say that mass 2 weighs 8 kilograms. Let's say mass 1 weighs 3 kilograms. So in our diagram, let's put a little 8 right here, a little 3 right there. Now, I think it's obvious that if you let these go, that 8 kilogram mass is going to come crashing to the ground. That 3 kilogram mass is going to get yoinked up. And before it hits the ground and comes to a stop, we want to see what's going on. We want to write the force equations, solve for the acceleration, interpret, and in fact, we're going to add a part D. Find the tension. So to write our force equations, and what we're really imagining, by the way, is that the string just continues in a nice straight line. If the pulley is massless and frictionless, it does. Let's label our forces. What are the forces acting on mass 1? Get the obvious one. Darn right. Tension. Mass 2g. Tension. Those are all of the forces. No normal force because we're not on any surface. Who's winning? got to be M2G. How do I know? Because I'm pretty sure the 8 is what's moving down. So I look at it and I say, what's that force? Oh, M2G is in the direction that 8 is accelerating. So for my force equation, it's going to look like this. M2G. Now I'm going to walk along the entire length of rope, Enzo. So when I walk, oh, and anything that ends up pointing down in my winner direction is winner, positive. Anything that on this side ends up pointing up, loser. So here, pointing up, loser, minus. But this tension, when I follow it to this side, which way does it end up pointing? Winner. And M1G, I thought it was going to be a winner, but when I follow it to this side, it ends up pointing up on this side, yes? Loser. Equals, normally it'd be MA. Did we look at more than one mass, Jordan? Then it's going to be mass of both times A. That H looks kind of warped. Let's try that again. Mass of both times A. Cole, if you're looking for a shorter way, you can also just go like this, by the way. Mass 1 plus mass 2. Because that's really mass of both. Just put it in brackets so that you know both of them are being times by A. And tension is vanishing. I feel tension leaving. I feel tension leaving. I feel tension leaving. Greg, if you want to, you can go to the bathroom now. Tension is gone. See, tension just left the room. Oh, sorry. No, come back. Finish the lesson. Come. That was just using you as my illustration for tension. Come on down. Come. 5 more minutes. Hey, there's my equation. What does B say to find? A said write a force equation. There it is. What does B say to do? You all have it in front of you. Do I have to really scroll up? What does part B say? How do you get the A by itself? More specific. Divide by what? The bracket. Yeah. So if I hear you correctly, Abe, and I think I do, you're saying it's going to be M2G minus M1G, that's the left-hand side, and divide it by mass 1 plus mass 2. 8 times 9.8, take away 3 times 9.8, all divided by 8 plus 3, or if you want to, 11. Folks, you want to practice typing these on your calculator because there's more than one number on the top. Brackets, there's more than one number on the bottom. Brackets, every year I got some meathead who doesn't try this during class and they get everything right on the test except the answers. And I know they were too dumb to bother trying this in class and figure out how their calculator works. What do you get? I don't think it's 75.72. The reason I know that is if it was in free fall, the fastest it could be accelerating is at 9.8. So I know the answer has to be smaller than 9.8 because that M2 is not in free fall. There's a rope tugging it back. I think this is the 4.454545454545454545. Yes? Greg, what's part C asking me to find? What do you think Exon is an abbreviation for? Folks, what do you think Exon is an abbreviation for? How about acceleration? Okay, so interpret the equation for the acceleration. The fact that we got a positive answer and we let mass 2 be the winner means we were right. Sometimes you'll think it's the winner and you get a negative acceleration. All that tells you is you guessed wrong. But it's an easy fix. Make every winner negative, every loser positive, and recrunch the numbers. It's a very quick fix. So C, we did. What does D, Enzo, ask us to find? What does D, Enzo, ask us to find? I added that, right? What did D ask us to find? Tension. I can feel it in the room right now. Find the tension. To find the tension, look at one mass. Which mass? Now here's your hint. The easiest mass is going to be the one in which the tension is the winner. So look at your diagram. In which one is tension the winner? I'm going to use mass 1. Trust me, I'll show you why in a second. So I'm going to use mass 1. Who's winning when I look at mass 1? Who's losing? My equation's going to be winner minus loser. And since I'm only looking at one mass, it's going to be M1A. Do you see why I picked the one where tension is the winner? Because to get it by itself, what's the only thing I need to do? Plus the loser over, which is, I think, easier than rearranging. So tension is going to be M1A plus M1G. It's going to be, what was mass 1? 3 times 4.45 plus 3 times 9.8. What do you get? 42.8?
Yeah.
Newtons. If you tried this with M2, your equation would be M2G minus tension equals M2A. You'd plus the tension, you minus M2A over. Trust me, when you crunch the numbers, you get the same thing. Your homework is work on the take-home quiz for the remaining 10 minutes. Yes, you may, Greg.